We start off trigonometry by just reviewing some basic things about algebra, and one of the most useful things for us is being able to classify numbers in certain ways. And one way that's really common to do that is with set notation, often called set builder notation. And so just take a minute to think if you know what this statement here says. This is not necessarily something that everybody knows right away, but it is useful, and it represents a way that we can define certain ranges of numbers, basically certain types of numbers or numbers that meet certain criteria or part of a certain set. The way we say this is that it's the set of all x, so it's like this is the set of all x such that x is greater than 0, right? And you can't really write this in another way. You can't say that, okay, you couldn't start listing out numbers and saying like, okay, that means it's 1, 2, 3. Like that's not right, right? Because any number, any positive number is greater than 0. And it's not just integers, right? It could be irrational numbers, it could be rational numbers. It could be, 0.000000001. That's greater than 0 also. So we can't list out all the things that are true about all the elements that are true. It's an infinite. This is what's known as an infinite set. Okay. If you wanted, if we can also define sets. We can set them equal to like a letter, so like kind of abbreviate sort of what's in the set. So if G is equal G, so we're defining G such as set X such that X is an integer greater than 0. Well, then we can start listing out elements of the set. And the way we do that is by listing 3 or 4 of the integers. This would be integers that satisfy that condition that it's greater than 0, and then having this dot 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 at the end to say that it keeps going like that, meaning the rest of the elements in that set meet that same criteria. And those are, so the things inside of a set are called elements. And then if we're asked to actually generate some of the elements in that set, let's say we call this set A. Then we could say another way to write this would be A is the set that includes, so positive even integers greater than 7, positive even integer greater than 7, 8, right? Another one, 10, another one, 12, another one, 14, and 3 or 4 is usually enough to establish, the pattern that of the criteria that define the elements in that set, and that dot 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 indicates that you would include all the other ones as well. And W such that W is an odd whole number greater than 10, or sorry, less than 10. Well, let's say B is that set. So B would include these elements. So an odd whole number less than 10, 1, 3, 5, 7, 9. But then that's it, right? You can't just keep going. You wouldn't put a dot 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 here. And so what we can see then is A, because of this dot dot dot, this ellipses here, that is a infinite set. Meaning it would keep going forever, has infinitely many elements in it. B, on the other hand, is not. It's finite. So there's not a dot 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 there. I mean, it only contains that many things. This would be this set here, if we call it C. There's not really another way that we could write this, because it doesn't specify that X is a certain kind of number. It's just a number. And so it's a real number. And we can't like enumerate the real numbers because there are infinitely many. Like where do you start listing real numbers greater than 3? Do you start at 4? Do you start at 3.5? Do you start at 3.00001? There is no starting point, right? It's infinitely close to 3 on the positive side. So that would be kind of a complete statement right there. Now, I understand that this is likely review for most people, but we can classify numbers as parts of different sets of numbers. And this diagram down here kind of represents, it's almost like it is a Venn diagram, essentially, that models where all these sets lie. And so if we're just looking at the real number system, the first numbers that we learned is like when we were in maybe preschool or kindergarten, we learned to count, and those counting numbers are also called natural numbers. Natural numbers are just like 1, 2, 3, 4, 5, etc. Okay, and then when we include the number 0, which the number 0 wasn't always a supernatural thing for us to know, when we add 0 to this, then we have the whole numbers. And then when we introduce negative numbers, right, negative integers, now we have, when we add in like negative 2, negative 1, 0, 1, 2, like that's integers. Rational numbers are, you know, stuff like 1/2, right? That's a rational number. It's a ratio of two integers. Those are like the numbers kind of in between. Those are the numbers like in between these numbers. And then those are rational. And then we also have these irrational numbers, which these elements are not part of the irrational numbers, because irrational numbers cannot be expressed as a ratio of two different numbers. So an irrational number might be pi, or it might be the square root of 2, or the square root of 3. Okay, those are numbers that we cannot express in another way. We can't express them as a ratio of two integers. And so all of those numbers combined, the rational numbers essentially and the irrational numbers, make up the real numbers. And so it's useful for us to be able to describe these some as subsets of another set. So if we have, for example, right, if we said rational numbers, so, or let's say integers, right? Integers, they are a subset of, that's the symbol for subset of. Integers are a subset of the real number system. Okay, and so we can say that integers are also a subset of the rational numbers. Natural numbers would be a subset of the whole numbers. Whole numbers are not a subset of the natural numbers, right? So we have to say which set kind of consumes the other set. One thing to keep in mind here is that all of these sets have infinitely many elements in them. Like you can count from 1, 2, 3, 4, and that goes all the way to infinity, right? 0, 1, 2, 3, 4, that's to infinity. Certainly, if that's the case, then the negative side also goes to infinity. So all of these are infinite. There's an interesting conversation about levels of infinity, like which are some infinities greater than others. And there's some really cool YouTube videos about that do a much better job explaining that than I ever could. But worth checking out for sure. Something that you don't really need to know. I mean, it's useful to know if you come across this, but if we want to, there are symbols that we use to represent these different number systems or number sets. So N is for natural numbers, and there's some embellishment on that letter N when we write it. Like there's actually like kind of a second little cross member there for the N. W, again with little stuff, that is the whole numbers. And then Z is actually with an extra little line down there, that is integers. Oops, sorry, integers. Q is what we use for rational numbers, and there's also, it's all kinds of stuff going on there. Rational numbers. And then I is irrational numbers. That makes more sense. Okay, and then real numbers is this R with an extra little thing right there. There's another type of number that we're not going to quite get into just yet, and it's called the complex numbers, and you do that with kind of like a C with an extra C on it, complex. And complex numbers are not part of the real number system, but real numbers are part of the complex number system. So it's kind of encompasses all things, and so that can be useful to kind of abbreviate things when we classify numbers. And so if we think about the square root of 7, like think about what we just talked about, what the different number subsets are, the number sets are. So how would we classify the square root of 7? Like, can this be expressed as a ratio of numbers? If the answer to that is no, it can't. Clearly it's not a natural number or a whole number or an integer, or and so then can it be expressed as a ratio of two numbers? No. So that means that this is irrational. 6 is obviously, if we think about what's the most concise way, like what is the smallest set that this thing belongs to, well then 6 is a natural number. pi, again, that's an irrational number. We know that pi cannot be expressed as a ratio. If you wrote out pi, it would keep going forever. You can't use a fraction to represent that. Negative 1.6, that can be expressed as a ratio of two numbers, right? For example, what would that be? That would be like negative 8/5, right? That's rational numbers. So this would be rational, so we call that Q. 0 is not part of the natural numbers, but it is part of the whole numbers. 2.4, again, similar to negative 1.6, that's going to be rational. And then 216, the most concise way to represent that would be as part of the natural number system. So this is just a way that we can quickly know like what kind of number is what. Where this really starts to become useful is if we're asked to evaluate expressions under certain conditions. So here's an example where we're asked to evaluate this expression x divided by the absolute value of x. And it says that assume x is a non-zero real number. Okay, so we know what non-zero real numbers are. They can be at either side of the zero on the number line, essentially, and everything else is fair game. Because, right, like we said, irrational numbers also are part of the real number system. And so if we kind of visually think about what that is, here can be the real number line, and here's 0, right? It's non-zero. So it can be anything over here, this would be positive, and anything over here, this would be negative. Another way to say that is that over here, x is less than 0, and over here, x is greater than 0. So what do we have to do here? Well, you have to also consider that the absolute value sign means a couple things. If you see a variable inside the absolute value sign, then that could mean that x is positive, x is negative, and x is 0. You kind of have to consider these three things. However, since we know that x is non-zero in this case, we only have to consider the case that x is positive and x is negative. So let's evaluate this expression in both of these scenarios. So scenario 1 and scenario 2. So in scenario 1, like let's say that x was negative, right? Then we would have negative x divided by the absolute value of negative x, which would just be x, right? So this would be negative x divided by x, which is negative 1. Okay, so if x is, if we have negative values for x, then x would be negative 1. Or sorry, this expression would evaluate to be negative 1. Okay, on the other hand, if we had positive values of x, we'd have x divided by the absolute value of positive x, which is just x divided by x, right? Whatever's inside here just becomes positive. That's how absolute value works. And this is just going to be 1. So what we would then have to say, how do we say both of these things? Well, we would say that this expression evaluates to negative 1, and then this semicolon it says whatever I write after this are the conditions that make this true. So this is for when x is less than 0, and it's 1 for when x is greater than 0. That's a greater than sign, not a C. So that's it. That is how you would have to answer that question. It could be two different things, and we know it's two different things basically because of the absolute value. Anytime you see an absolute value, and some absolute value sometimes considered scary by students, but there's nothing really to be worried about. You just know that two different situations could be the case. So this should be definitely review here, a problem like this. All that's being asked is that you evaluate this expression for when x equals 1. So go ahead and pause the video and see if you can solve this and get the correct answer. I'm going to go ahead and solve it right now, but you should try to solve it on your own. So first step here, if I know that x is 1, I'm just going to go ahead and plug 1 straight in for every time I have x. Now if there were instances in this problem where I could combine x's together, I would do that first. That would save me some time substituting the number in for the variable. But for now, I can't do that here. There's no way to combine any x's, so I may as well just plug in 1 first. So I'm going to say 3 times 6 times 1, that's what x is, plus 2, minus 5 times 1, that's what x is, minus 4 minus 2. Okay, you can definitely evaluate the parentheses first, like the 4 minus 2, and make that 2, but it's fine at this point. Substitution and parentheses, the order in which we do that won't matter. However, now we definitely have to follow the order of operations. So parentheses wise, the first thing that we see, we have 3, right? And then inside this parentheses there's a multiplication, so 6 plus 2, this would be 8, minus 5 times the 1 is still there, and inside this parentheses 4 minus 2, that's 2, right? So now we have 3 times 8, which is 24, and then we're subtracting from that 5 times 1 times 2, which is 10, right? So 10. So now all we need to do is say, we have 24, we're going to take away 10, so we're left with 14. So 14, oops, sorry, I almost crossed it out there. That is the answer to this. That is how you evaluate this expression. All right, another similar problem. You can go ahead and pause the video and see if you can evaluate this correctly. Now, I would recommend plugging these numbers in first, these values for x and y. You don't have to, though. You could distribute. You could use the multiplicative. You could use the distributive property multiplication to multiply out these two binomials, right? Use the distribution here, and you can come up with a large polynomial that you can combine like terms on and then substitute in later. But that's going to end up being more work. It's not going to be wrong. You won't get the wrong answer at the end, but there will result in more places for you to potentially make a mistake. So it's nice since we have these numbers, and then we'll be able to have integers inside of these parentheses that we can then combine before we do any multiplication at all. Well, before we do any like large number multiplication. So we will have, so like if we do that, if we write these simplified out, we'd have 3 times 2 times 4, right? X is 4, minus 3 times y is negative 2, okay? And then we'd multiply that by x is 4 plus 4 times, and then y is negative 2, okay? And then over here we saw 5 minus 2 times, and then y is negative 2, so negative 2. And then we will have 3 right here. Okay, so what do we do here? Oh, sorry, x, I had x's, not, sorry, I need to fix that. One moment. This would be 4, not negative 2. Okay, so now we have 3 times 2 times 4 is 8, minus 3 times negative 3 times negative 2 is a positive 6, right? So that's 6. And then in this one we have 4 plus 4 times negative 2 is negative 8. So let's say it's minus 8. Right, minus 8. Let's just write the minus. Okay. Then we have this part, so it's 5 minus 2 times 4, which is 8, and then 3 on the outside. And we can simplify again. We say 3, 8 plus 6, right? This is parentheses still of the order of operations. So 8 plus 6 is 14. 4 minus 8 is negative 4. And then 5 minus 8 is negative 3. We still have that 3 out there. Now we can multiply. So 3 times 14. 3 times 14 is 42. And so we have 42 times negative 4, right? 42, just separate this in steps still. And then negative, so minus negative 3 times 3. And minus a negative is like plus a positive, right? So then 42 times 4, negative 4, sorry. 42 times negative 4 is negative 168. Plus 9. So this is going to equal, right? It's going to evaluate to negative 159.